This is a diagram of a NPN transistor, and on the left drawing you can see that it's labeled collector, base, and emitter, and on the right drawing you can see that the base is the signal input and the output is the collector. And I'm going to build a mock-up using a single NPN transistor to demonstrate what the biasing resistors do in an audio amplifier circuit. This is the wiring diagram of the mock-up. All the way to the right is the battery supply, which is two 9-volt batteries in series for a total of 18 volts. At the bottom middle is R1, which is 150 ohms, and C1, which is a 100 microfarad capacitor. Above that is the NPN transistor, and above that is R4, which is 33k ohms, and that is the load resistor for the NPN transistor. To the left of the transistor is R2 and R3. This is the voltage divider circuit that makes up the biasing network for the NPN transistor. And in the mock-up, those are actually 4 resistors. R2 is a 100 ohm resistor and then a 100k ohm variable. R3 is a 1000 ohm resistor and a 100k variable. And the reason for that is when I vary the resistance, I cannot go down to zero resistance, which would short out the battery, and also I could potentially damage the transistor. And to the left of the biasing resistors is C2. That is where the input is going to be applied to this amplifier, and it is a .02 microfarad capacitor. This is the mock-up on the workbench. And if we go all the way over to the right, that is the 18-volt battery connection. Here is R1 and C1. This is the NPN transistor. And this is R4, the load resistor. This is R2. And this is R3. And here is C2, our input capacitor. Let's take a look at R1 and C1. What that is doing is it is raising the voltage a little bit from ground of the emitter of the NPN transistor, which also influences the bias of the base. And those two in combination is acting just like a battery. So we can see what's going on in this circuit. I'm going to monitor this amplifier in 2 places. As you can see, I'm going to have a voltmeter connected to the base of the transistor, and I'm going to have my oscilloscope looking at the output on the collector of this NPN transistor. Okay, here's the setup. Okay, now I've got the 18 volts connected to the amplifier, And I have set the bias resistor so I have a nice signal at the output of the collector, and I measured the resistance of each, and R2 is 14K and R3 is 34K. Now I'm going to lower the resistance on R2, and the reason why it's jumping is that's the DC level changing, and you can see that the voltage has dropped to about half a volt to down to almost nothing, less than a volt bias. So I'll bring that back up to almost 6 volts again. Okay. Now I'm going to lower R3. See it, the voltage level is jumping in the other direction, and now the bias is getting higher. Notice that it's starting to clip. Now the signal's gone altogether. Okay, I'll lower this back down to about 6 volts. The two adjustments that I made on the biasing resistors, the first one was to lower the resistance of R2. And when I did that, the signal got smaller, and that's because the signal is being shorted out, it's going to ground, and also the NPN transistor, the bias is so low, it's actually turning off the ability of that NPN transistor to conduct. And when I lowered the resistance of R3, we saw that the nice signal started to flat top and eventually disappeared. That's because the base of the transistor became so positive that it drove that NPN transistor into saturation, which means between the emitter and the collector it turned into pretty much a straight wire. So when the bias resistors are chosen correctly, in this case R2 is 14K and R3 is 34K, we have a nice signal at the output. And also the resistance of both of the bias resistors are high enough that they do not short out the signal. And I got this information from engineering books and also looking at other audio amplifiers.